So far this semester, we've looked at integrals over curves, which gave us line integrals. So those were integrating over a one-dimensional domain. We've also looked at integrals where our domain was in the plane. So we looked at those in rectangular and polar coordinates. And we also looked at integrals over surfaces. So what we're going to do now is we're going to move up one more dimension to look at integrals over three-dimensional objects. So we're going to integrate over volumes here. So let's look at a motivating example to why we might care about such a thing. So suppose we have a solid W of volume V measured in meters cubed. And suppose the density of this solid is a constant rho all throughout the solid and is measured in kilograms per meter cubed. And we learned from elementary physics that the mass of the object W is given m is equal to rho V, where rho is the density and V is the volume. Sorry, that V should be capitalized there. And we notice in here that if we match up the units, this has units of kilograms like we would expect. So the natural question is well, what happens if our density is not constant? Because certainly it's much more likely that a density not be constant over a region than it is constant. So we'd like to still be able to calculate the mass in that case. So let's look at the simplest possible shape. So we'll take a solid box W. And here I've made the box to be one in the x direction, one in the y direction, one in the z direction. So simplest setup we could come up with. But let's suppose that our density isn't necessarily constant. So at any point x, y, z in the box, the density at that point is given by some function rho of x, y, z. So it certainly could be that rho of x, y, z is constant, but it doesn't have to be. It can vary at each point in the box. You could have a different density. So the question we want to answer here is how are we going to calculate the mass of the box when we have this density rho x, y, z that's varying? So if we think back to how we calculated work for a non-constant force over a curve, or how we calculated flux when we had a velocity of a fluid that was varying going through a surface, we approached those problems in the same way. We broke the things up into small pieces. So for the line integral, we broke the curve up into small pieces so we could say the force was approximately constant on each piece. And similarly for the flux, we broke the surface up into small pieces of surface where we could assume the velocity of the fluid was about constant on each piece. So we want to do the same thing here. We're going to break that box into smaller pieces so that the density is approximately constant on each of the pieces. So this is one of the important concepts to take out of calculus courses is when we have something like this that we don't know how to calculate, we can approximate it by breaking things into smaller pieces. And doing that process and letting the pieces get smaller and smaller is what leads to integrals. So let's take the simplest possible first step. So let's take those intervals of 0 to 1 for x, 0 to 1 for y, and 0 to 1 for z, and we'll break each of those up into two smaller subintervals of equal length. So this is going to break our box W up into 8 smaller boxes. So if we've broken the x interval from 0 to 1/2 and 1/2 to 1, and similarly for z and similarly for y, so we have these 4 boxes here in the front and 4 boxes in the back for the total of 8 smaller boxes. And we're going to label these boxes as W with a subscript ijk. I is going to correspond to the x direction, j the y direction, and k the z direction. And this is a bit messier to index because we have three dimensions here to work with. Let's go ahead and see what I mean by this indexing. So for the first one, we're saying W0, 0, 0. So this is moved 0 in the x direction, 0 in the y direction, and 0 in the z direction for this box. To get this box, we have to move 1 in the x direction, 0 in the z, and 0 in the y. So we have a 1 for the x, 0, 0 for y and z. And similarly for this one, we've moved 0 in the x, 0 in the y, and 1 in the z. This one's gone 1 in the x, 0 in the y, 1 in the z. And then these ones in the back here would be labeled similarly, but now we'd have 1 in all of the y coordinates because we've moved 1 in the y direction for each one of those. And that's how we're going to label our boxes. So for each of those boxes, we're going to pick some point xi star, yj star, and zk star that's inside the box. You can pick those wherever you want as long as it's inside the smaller box wijk. And so what we're going to do is we're going to say that that box wijk has approximately a constant density of rho xi star, yj star, and zk star. Certainly the density doesn't have to be constant, but we'll approximate it as constant. And we'll see as we get smaller and smaller boxes that approximation becomes better and better. Note that the volume of each of these boxes is delta x, delta y, delta z. And in this case, since we've broken each of the intervals up into two equal pieces, each of these is 1/2. So we have the volume of each small box being 1/8. So now our mass is, we're going to sum I goes from 0 to 1, j goes from 0 to 1, and k goes from 0 to 1. And we take the approximate density and the volume of each of those smaller boxes. And so we get this thing here. So notice that each of these has two terms. So there's 2 times 2 times 2 terms. So there's 8 terms total. So we'll see this in an example next to see how this actually works. It's a bit of a mess to write out by hand. So let's go ahead and let's let rho be the function just x, y, z. That's our density function. And now when we pick our values here, remember x0 star has to just be anything between 0 and 1/2, including the edge point. So I take that to be 0. And x1 star has to be anything between 1/2 and 1. So we'll just pick that to be 3/4. And similarly, we pick some other values. You could pick anything here. These were just the ones I happened to choose. So then if we write this out, we have the row of 0, 1/2, 0. So it's x0, y0, z0, and then the volume 1/8. And then I go x0, y0, z1, and so on. So you see we get all 8 boxes here. You can check that. And then we just plug in for the function. So since it's x, y, z, anytime there's a 0 in any of the coordinates, that'll just give me 0. So we're really only going to get 2 coordinates where there's not 0 at all. That's going to be, we have to have x1 in the x coordinate, and then we can take y0 or y1, and then we have to have z1. And so in that case, with this example, for this particular function and these particular choices of our points in the smaller boxes, we get the mass is about 9/128. So you can see this is essentially just like doing a Riemann sum from Calc 1 or Calc 2, where the only difference is here we've got more variables, so it just gets a little messier. Now, just like in Riemann sums for Calc 1 and Calc 2, if we use more boxes that are smaller, we're going to get a better approximation, because saying the density is approximately constant on a smaller box is definitely more accurate than saying it's approximately constant on a big box if it's varying. So here we can see we broke this up into, I think, 10 boxes in each dimension. So we'd have 100 small, or 1,000 small boxes in this case. And the sum would be just the same. And we can just take this to be n now for any n. And so if we let the delta x, delta y, and delta z go to 0, which is the same thing as letting the number of small boxes go to infinity, we end up with the exact mass, because as they get smaller and smaller, we get a better and better approximation. So we denote this limit. So notice this thing on the right is now we're taking a sum over n boxes in each dimension. So we have n cubed boxes, and now we're letting the delta x, delta y, and delta z go to 0. So that's making the n go towards infinity. Of course, you could use different numbers of boxes here. I'm just choosing n for all of in each direction just to make it a little simpler. And we denote this Riemann sum here, limit of Riemann. So this thing inside here would be a Riemann sum. The limit of this Riemann sum is our integral here. So we're integrating over our box w, so we put a subscript w on the integral. We're integrating this density function, that's our function here, and then the dv is the incremental volume, the delta x, delta y, delta z. So this is our notation for this mess over here. In this case, we can also write it as an iterated integral. Remember, we did this for integrals in the plane when we were doing two variables, where we'd have a region R, but we'd write it as an iterated integral in terms of dx and dy. In this case, since we're integrating over three variables, we get three integrals in the iterated integral, which is why we're calling them triple integrals. So in this case, I just did dx, dy, dz, and each of them goes from 0 to 1. Of course, you could change the order on those. Since we don't know what rho is, we don't know what the best order to do these integrals is. And so, of course, that worked fine for a box, but just like we could do more general regions in 2 space, and just use squares, and those squares, as they got smaller and smaller, would approximate the region better and better, it's the same thing for a general region in 3 space. Our boxes won't match up perfectly for a general region, but as the boxes get smaller and smaller, it becomes a better and better fit. So just like we had integrals over regions R and R2, when it's a general region, remember those limits could be pretty hard to come up with and get pretty tricky. It's the same thing here. When we have a general region W in R3, finding those limits can be quite tricky. So we'll be spending some time on that in class. This video just gives you a little motivation for why we actually care about triple integrals by relating it to a problem in physics, and also shows what do we mean when we're saying this triple integral in terms of a Riemann sum.